Hello again, friends. Welcome to my home. Today, we've introduced indefinite integrals. Excuse me. And we have all of the derivative rules that we already remember. Um, and so if we can match an indefinite integral or a definite integral to one of the derivative rules, we can go on pretty fine. But today we're going to talk about specific techniques we can do to help us make those matches. What I'm going to call integration techniques. And, well, what you can be integrating gets kind of complicated. We'll get into that. Of course, we have our basics, right? These are things that you've been doing for the whole time. And at this point, maybe you don't even need to do it explicitly anymore, right? We've got this 3 cosine x, and we know that if we have an integral, we can take that 3 out, put it in front, and do the integration here. So the integral of cosine x dx is, of course, sine x plus c. So we get 3 sine x plus c, right? Some of you might be comfortable enough with integration that you don't even have to write out this step. You can just kind of do it. Now, that's not to say factoring out doesn't have its uses. Sometimes you might want to do it just to kind of keep everything sorted out and make sure you don't forget anything, right? So here we've got a fraction. And as soon as we got fractions, sometimes they can get kind of complicated. You don't know what might cancel out, all that other stuff. So we're going to factor out that fraction. So this becomes 6/7 integral of x squared dx. Take that integral, you have 6/7 times 1/3 x cubed plus c. And we can kind of cancel that through and see that this becomes 2/7 x to the third plus constant, right? So again, neither of these are groundbreaking. You might have to do it just as kind of a bookkeeping, make sure you don't forget. That's good. And then, of course, there's the, you're going to hear me saying this a lot, integrating term by term. So that's just noting that whenever two terms are separated by a plus or a minus, they don't really interact. So you can take the integral of one without worrying about the integral of the other. So we look at this, and we say, oh, what's the integral of x cubed, the fifth root of x cubed? The way we're going to do that is we're going to change this to x to the 3/5, and we have 2x dx. Technically, I should put parentheses around here, and then we integrate this part, use the power rule, add 1, it becomes 8/5 as the power, and then we have to divide by 8/5, which means multiply by the reciprocal, so that's 5/8, and plus integral 2x is just x squared plus constant, right? So when I say integrate term by term, I mean look at it, this one, then do this one. Don't let them bother you. Point of order, and this will come up in a little bit. If you ever need to integrate, if you're doing indefinite integrals of 1 over x, I know you, or anything like this, this is just a side note. You're going to get ln, of course, but always put absolute value bars around the x. This has to do with the fact that, typically when we talk about this, it's defined on the positive numbers, but since you're taking an indefinite integral, it's not clear whether you're talking about positive or negatives. So to ensure against that, since natural log is defined only on positives, we introduce absolute value bars. So you're going to be seeing that later in the video. That's why I do that. Okay. So those were the basic things. And then the next level is just the manipulations that we have to do to use those basic things. So the first level is multiplying out. And that happens in a lot of cases, but in this case, when we got binomials multiplied together. So we got x plus 3 times x squared minus 1 dx. We're integrating that. That doesn't fit anything on our sheet, so we're like, I don't know. Well, if you multiply out using the distributive property, you get the integral of x to the third plus 3x squared minus x minus 3 dx. And then this can be integrated term by term. So that becomes 1/4 x to the fourth plus x to the third minus x squared over 2 minus 3x plus a constant. Kind of a mess, but you know, we got there. Similarly with this, this is like, that doesn't fit anything on our derivative rules sheet, but if we acknowledge that this is the same as 3x plus 1 over 5x times 3x plus 1 over 5x dx, a little bit of distribution will make that equal to the integral of 9x squared through this plus 6/5 plus 1 over 1/5 x squared dx. Now that it's multiplied out, you can again multiply this or integrate it term by term. So this becomes 3x cubed plus 6/5 x minus 1 over 25 x plus a constant. Alright, so that's multiplying out. If you have things that are multiplying each other, try multiplying them out with the distributive property, and then go term by term. Next level, splitting a numerator. So we have something like this, and we're like, that doesn't fit anything. But one of the things, if you have addition or subtraction in the numerator of a fraction, you can rewrite it as two separate fractions. This you can rewrite as x squared over x plus 1 over x dx. This reduces to, of course, x plus 1 over x dx, and then once again we integrate term by term. So this becomes x squared over 2 plus the natural log, the absolute value of x, plus a constant. So yeah, make use of splitting a numerator. It's just another avenue of going term by term. You know, approximately equal to multiplying things out, but you're dividing things out. Warning! This works only on a numerator. A lot of people get really confused with fractions when you have addition in the denominator and you can't really do much. I've seen, this is one of the most common examples I've seen. It goes at all levels of math. Well, people see an x here and an x here and somehow think they can cancel them out. And that's not it. Don't do that. Try not to do that. I know it's hard. But, so you can't split it, you can't cancel anything. What can you do here? Well, here's another technique. You can use the fact that you can always add or subtract the same number, or you can use polynomial long division. So for simple things, you can just do an add and subtract. This becomes the integral of x plus 1 minus 1 over x plus 1. Then, once you've done that, you can split it, right? So you comes the integral of x plus 1 over x plus 1 minus 1 over x plus 1. This is just 1, you integrate term by term. So it becomes x minus the natural log of the value, x plus 1, plus c. This is much more complicated. Add, subtract is not going to help us too much here. What we're going to use is PLD, polynomial long division. If you remember synthetic division, please use it. It's much faster and much better. You're less likely to get confused. I don't know what your pre-calc class is like. Maybe you don't remember either. So we're just going to show you how that goes. We're taking this polynomial and dividing it by this polynomial. So we have x cubed. Always put in the missing x squared term for the 0. Minus x plus 2, and then you're dividing it by x plus 1. And long division is just a series of multiplications and subtractions. You ask yourself, what do you have to multiply x by to get x cubed? Well, x squared. And then you multiply this by x squared, so you get x cubed plus x squared, and then you subtract. These cancel out, you get negative x squared minus x. And so you're like, oh, what do I have to multiply x by to get negative x squared? Negative x. You subtract, you get 0 plus 2. There's nothing here. You just have a remainder of 2. So what does that give us? That means that this fraction can be rewritten as x squared minus x plus 2 over x plus 1. Now that when you've done that, you can integrate it term by term. Kind of running out of room here, so if you'll allow me, I'll write it up here. Integral of x squared is 1/3 x cubed. Then we have minus x squared over 2, and then plus 2 natural log absolute value of x plus 1 plus c. If you remember synthetic division, please use synthetic division. You can do this same calculation in a lot fewer steps in writing. All right. Next, use some trig identities. The major trig identities that you should remember above all else. If you can only remember one, it should be sine squared x plus cosine squared x equals 1. If you can remember more than one, you might also want to add in tangent squared x plus 1 equals secant squared x, and then 1 plus cotangent squared x equals cosecant squared x. So that's if you can only remember 3. If you can remember more, there's more to remember. But let's get to the one at hand. You see one that doesn't fit any of our rules. But I see a 1, I see a sine squared, so it's worth coming back to this and trying to fit it in here. There's a couple ways of doing it, but probably the one you're going to see most is to do some algebra on this. And if you subtract sine squared from both sides, you'll see that, oh, you get cosine squared x equals 1 minus sine squared x. Oh, I have 1 minus sine squared x. So this is the same as the integral 1 over cosine squared x dx. What is 1 over cosine squared? Well, that's the integral of secant squared x dx. And that fits our sheet. So that's going to be tangent x plus c. Right? No big deal. We're using our trig identities. Moving forward. What else can we do? Well, here we have something. Doesn't fit any of our answers. Doesn't fit a trig identity. What can we do? Well, we can use the conjugate. So if you see something that, whatever you have, like it needs to get squared, especially if it's on the denominator. It's got a plus or a minus. What you want to do is multiply by a fraction that's made up of the conjugate. So 1 plus sine x. But of course, you have to have that on the top as well. So this becomes the integral of 1 plus sine x, and if you don't remember, multiplying by the conjugate, you get the first term squared, so 1 squared is of course 1, minus the second term squared, which is sine squared x. From a previous slide, you should remember, because it wasn't that long ago, that 1 minus sine squared x is cosine squared x. And then we can split the we're using all sorts of techniques here. So like, still doesn't fit, but we can split the numerator and go term by term. So this is 1 over cosine squared x plus sine x over cosine squared x dx. A little bit of algebra should show you that this equals secant squared x plus secant x tangent x. And both of those are your derivative rules. So this would equal x plus secant x plus c. See? Well, again, these things get complicated in a hurry. Already we're using one rule sets off another rule, sets off another, or one technique gives us the opportunities, another technique gives us the opportunity, the third technique, and only then do we really have a chance to grasp onto this. Alright, with the next video we're going to go into the most powerful technique that you'll learn in an AB class, and that's substitution. And substitution is a way of clearing away the complicated parts so you can deal with something that's a little bit more simple. But again, that's next time. In the meantime, thank you for stopping by.